Hi, I'm Desiree,
I'm Mira.
and we're the CNARC research team. CNARC stands for Coagulant Nanoparticle Attachment Rate Characterization, and as the name suggests, we're looking at determining the rate at which coagulant nanoparticles are attaching to flocculator walls and clay particles in the Agua Clara system.
Agua Clara plants rely on coagulation and flocculation to ensure that water meets its quality standards. Coagulation and flocculation are processes by which coagulant nanoparticles are added to untreated water. The coagulant nanoparticles then collide with and attach to contaminant particles, forming flocks. However, if coagulant nanoparticles do not attach to the contaminant particles, the free nanoparticles tend to attach to and accumulate on the walls of the flocculator. This presents several problems for Agua Clara plants. Firstly, as you can see in the diagram, it reduces the diameter of the tubing, which in turn increases head loss in the flocculator. And head loss is the energy dissipation that occurs as water flows through a pipe. Increase in head loss needs to be compensated for by increasing the energy demands of the plant. Another issue is that coagulant is wasted, and this needs to be made up for by adding more coagulant.
So while this is the first semester for CNARC research, the idea behind the team came from observations seen by other older teams. This is a graph from an old contact chamber team, and they observed an increase in head loss across the length of their flocculator. We're more concerned with the rate of head loss accumulation and how that changes across the length of the flocculator. We expected to see that in the first section there'd be the greatest rate of head loss accumulation, and that rate would decrease across the length of the flocculator. We also varied the turbidity to see how that would change the trend. With that, we expected to see that with a decreasing turbidity, there would be a higher rate of head loss accumulation. Overall, our main goal was to determine how fast coagulant is attaching to the flocculator walls.
This slide shows the experimental setup CNARC used this semester. Water flows in through the influent pipe and is pumped into the flow accumulator. The flow accumulator dampens any fluctuations in the water caused by the pump. The water flows out of the flow accumulator, after which clay is pumped in. The rate at which clay is pumped in is controlled by the PID controller, and this is determined by the target turbidity. And the turbidity is measured by the turbidimeter. Water then flows out of the turbidimeter, after which coagulant is added at a constant rate. And the coagulant, clay, and water mixture then flows through the cold flocculator and exits the system through the effluent line. After each experimental trial, the air pump introduces air bubbles into the system in order to clean up any buildup of coagulant on the walls of the flocculator, and this entire system was automated through Procoda.
Obviously, the most important aspect of our experimental apparatus is the modified coil flocculator. To do this, as seen here, we just took a regular coiled flocculator that a lot of other research teams uses, and then we attached 4 pressure sensors along equal lengths of the flocculator, and this allowed us to see how in each section of the flocculator the rate of head loss accumulation changed. In that little sub-image and also right here, you can see the connection we used to attach the pressure sensors to the flocculator. One change from symposium season is that we changed our pressure sensors from the 200 kPa to the 7 kPa. We did this in order to get a little bit more sensitive results and hopefully better results.
This slide shows the results obtained by CNARC. This is a graph for head loss over time for the different sections of the flocculator, and these were results for a target turbidity of 40 NTU. However, these trends were visible for all target turbidities that CNARC used. The first observation made is that over time, head loss increases in all the sections of the flocculator, and this is because as the experiment progresses, coagulant nanoparticles attach to and accumulate on the walls of the flocculator, decreasing the diameter and thus increasing head loss. A second observation made is that along the length of the flocculator, the rate of head loss accumulation decreases, and this is seen by a decreasing slope for each section of the flocculator. The first section of the flocculator experienced the greatest change in head loss, and this has the greatest slope. However, over the subsequent sections of the flocculator, this rate of head loss decreased. And this is because in the first section of the flocculator, fewer clay coagulant flocks have formed, and this means that there are more free coagulant nanoparticles to attach to the walls. Secondly is because most of the free nanoparticles have attached to the first section of the flocculator, there are fewer free nanoparticles available to attach to the subsequent sections.
As I mentioned before, we were also looking at the effect of changing the turbidity levels. We expected to see that with decreasing turbidity, we would have increased rates of head loss accumulation. This is because turbidity is related to the clay concentration, and when there are less clay particles or lower turbidity, the coagulant is more likely to attach to the walls and thus increase head loss. However, for the first experiment that we ran in the first section of the flocculator, we saw an opposite trend. We're not really sure why this occurred. It's possible that it's not only clay nanoparticles or coagulant nanoparticles that are attaching to the flocculator walls, but a clay coagulant mixture. And so that would explain why at higher turbidities, where there's more clay that it could also attach to the walls, there'd be a higher rate of head loss accumulation. But that's sort of speculation, and more experiments need to be run in order to confirm that. But as you can see in the second and third section of the flocculator, there was in fact an increase with decreasing turbidity. So that supported our hypothesis. In terms of future tasks, we ran a second experiment, but we noticed that throughout the experiment, clay was settling in the tubing before entering the flocculator, as you can kind of see in that image. Below the red line, there's a layer of clay that has settled out, and above it is just like a water and an air bubble mixture from the cleaning step. And so this is a concern, because that means because the clay is settling before it enters the flocculator, we don't know the actual concentration of clay in the flocculator, which skews with our results and means we can't really trust our results. So future teams are going to have to troubleshoot that issue. Another thing is we kind of want to determine what is the best place to add coagulant. Right now we're adding it right before the flocculator, but perhaps it'll be better to add it a little bit before that so the clay and coagulant can interact a little bit more before entering the flocculator. Future teams will have to sort of experiment with that. But after troubleshooting those issues, future teams can continue running experiments to determine the forced surrey rate constants for the loss of coagulant to the flocculator walls and to clay particles. They'll also have to vary the velocity gradient for that. But we're excited to see how the future of this team progresses. Thank you, and if you have any questions, you can email us or send us a GitHub issue. Or also read our report for more information. Thanks again.
No.